Hello. Yeah, so I think probably we can start. So let me first just a minute. Let me first introduce you. And yeah, so let me first introduce Professor Divya Oberoi. So Professor Divya Oberoi is from NCRA TIFR. So he completed his PhD from ISC Bangalore and NCRA, and then he moved to France and USA for postdoc. And then he finally returned to NCRA and he's working on the solar physics. Till now, you guys have understood, or you guys have already attended lectures on optical and X-ray observations and UV observations. And today he will be talking about the other end of electromagnetic spectrum, that is the radio observations. And I think multi-wavelength observation is incomplete without radio observations. So this talk is actually very, very important. And we were not having, this talk in previous workshops. So I think it will be very, very useful to have, as well as also it will be complementary to Aditya, which do not have any radio measurements instrument. Okay. So with that, I would like to thank Divya for kindly agreeing to give this talk to you guys. Please make most of it. And if you want to ask question, please remember you have to use the mic. Okay. Otherwise, he won't be able to listen. Yeah. Okay. So Divya, please go ahead. Thank you.
Great. Yeah. Thank you so much. Thanks a lot, Webhouse. Thanks also for setting the stage for this talk, and also giving me this opportunity to talk to the next generation of solar astronomers in India. So I'm sorry that I'm not able to join you in person, and I'm having to give this talk remotely. It was just not feasible for me to come over, even though I like Nainital quite a lot. Okay, so this is going to be a sort of informal talk, in the sense that I don't have a set syllabus to cover or something like that. And so questions are welcome. I know the online format makes it a little harder for you to ask questions in the middle of the talk. I don't know exactly what the setup is like, but if it is feasible for you to ask questions during the talk, you're welcome. If I think it'll take me too long, or it'll be a digression, then I'll push it to the end. Otherwise, I'll try to answer it right there. Okay, and I believe that this is the first talk which is going to be talking about the radio part of the spectrum. So I'm going to start from sort of basics and not assume too much background about the radio aspects of solar observations. Okay, but before I get into what I'm really supposed to talk about, I wanted to share, some personal reflections about astronomy and how I got into astronomy and what I really love about it. Okay, so the only single assumption which astronomers make is that the laws of the physics are same everywhere in the universe, right? Whether you are on the Earth or some other planet in the solar system, or in the neighborhood of some other star or some other galaxy, or maybe many billion light years away from here, the laws of physics are the same. The fine structure constant, its value is the same. The capital G of gravitation, Newton's gravitational law, its value is the same, and so on. And apart from that, everything else we are able to derive from our observation. And it's very impressive that we are able to do this despite very severe limitations under which we operate. So, for example, unlike many other branches of science, you cannot really go to the place you want to study, right? Okay, you can go to the moon, you can send your probe, which can make in situ measurements. Now, Parker Solar Probe can touch the corona and so on, but that's still very limited, right? You cannot really make the sorts of measurements which you routinely do in your labs, do the kind of experiments where you hold all of the parameters constant, vary just one, and try to figure out what the laws of nature might be, etc. And you cannot even look at a given object from a different perspective, right? You are confined to this Earth for most of your observations, and you just have to wait for light to come to you. And whatever you are able to see out of this electromagnetic window is all that you have. Okay, now you also have neutrinos and gravitational waves and energetic particles, but the bulk of what we know is still from this light, right? So the job of the astronomer is to really characterize this light in the highest precision possible. And because nobody else shares that need, it automatically puts you, at the forefront of technology as far as characterization of light is concerned. So telescopes tend to be, really amazing feats of engineering. And so when I was sort of in my BSc, second, third year, and so on. I was reading a lot of Sherlock Holmes. I was also working with somebody a bit senior to me on doing some experiments in astronomy. And it seemed to me that astronomy was really, the science and a bit of art of making the most accurate measurements you possibly can. And then using this framework of laws of physics, which we have, to arrive at, a logical deduction. So it seemed a little bit like playing Sherlock Holmes, right? The crime has been committed, the murder is done. You now have the evidence in the form of light, which is coming to you, and now you have to reconstruct the crime scene. So that's sort of how I used to look at astronomy. I found that really fantastic, and I was lucky enough to get into a career which allows me to do that. Okay, so with that sort of some sort of a preamble, nothing to do with solar radio astronomy, let's get to what I'm really supposed to talk to you about. Okay. This is an observed spectrum of the sun in blue, which I'm sure somebody or the other might have shown by now. And we have all been taught that a solar spectrum or a stellar spectrum resembles that of a black body. And you can see that it is pretty much the case, at least in this long wavelength part beyond the peak. The spectrum is very close to the black body spectrum. And as you go to the short wavelength part, you see departures from that. And if you look at this region, right, this of course looks nothing like a black body spectrum. And this, most of what you have heard till now is from this part of the spectrum, right? It's the, a little bit of optical, and then near UV, far UV, and then X-ray and so on. We are going to be talking about the other end of the spectrum, right? So if I sort of was to put things in perspective, radio regime lies somewhere here, and this is the same black body, idealized black body spectrum, which I was showing you in the earlier slide. And these numbers are, these are to scale, this plot. So in the optical, if I'm looking at something like 10 to the power 8 in whatever these units are, by the time I'm at a wavelength of 1 meter, I've gotten to something like 10 to the power minus 16, right? So you naturally wonder if the object which I'm trying to study, if it is emitting only 10 to the power minus 24 times its emission at the wavelengths which I'm interested in, why the hell am I going there to study that, right? Why should I not study the sun at frequencies or wavelengths where it is emitting most of its radiation, right? So the answer to that question is in the following slide. So you all know now that on top of the sun sits the chromosphere and then the corona, right? And the corona is a huge expanse of plasma, which is at a temperature of about a couple of million Kelvin, right? So what happens is that as you go to longer and longer wavelengths, somewhere around centimeter wavelengths, you begin to see the corona. The corona is no longer transparent to these radio waves, or its emission measure has become significant, or its optical depth has become significant, that you begin to see it. And so the spectrum of the sun no longer looks like this black body spectrum at 6,000 Kelvin. It begins to look something like this, right? This is an artist's impression, but it is pretty close to what the reality is like, right? So it begins to approach the black body spectrum of the corona, which is at 1 million Kelvin. And now you realize why you must study the sun at these frequencies. But if you wanted to study the corona, these are the only frequencies here where you can see the corona in emission, right? You can look at, of course, coronagraphs, and you have seen, of course, numerous examples of that. And there, what you are looking at is the light from the sun scattered off the electrons, the Thomson scattered light from the coronal electrons, right? So that does not tell you as much about, the physics of what is happening in the corona. It tells you essentially number density, and that's about all it can tell you. But here you are now able to see the emission from this corona. And these are the only frequencies in the electromagnetic spectrum where you will see this emission. So if this is what you want to study, then you have no choice but to come to these radio wavelengths. You'll also notice another curve which I've drawn on top of it, which I've labeled the active sun. That's actually a little incorrect. It should have risen to something like 10 to the power 13 here. That's the highest brightness temperature which we've seen so far from active emissions. So these are, so just like when we were looking at the earlier plot where in the EUV, you had a large departures from the black body radiation. Here also, it is the same active emissions which are giving rise to the departure from this million Kelvin black body of the corona. So this emission is not present all the time, of course, and this is not meant to be a single episode of activity does not give rise to this. This is a sort of upper envelope of all the activities which you would ever see on the sun. That kind of becomes so much brighter. So now you can see that if there is something which the temperature of that is, approaching 10 to the power 13 Kelvin, that naturally cannot be the physical temperature of that system. There must be some other reason for that temperature to be so high. And that's something we will come to as we go ahead. Okay, just to establish a little bit more background. So the Planck's law you're all familiar with. We just saw the black body spectrum. Here are the two forms which you typically use of the Planck's law. At radio wavelengths, we are operating in this regime where the h nu by kT is much, much smaller than 1, right? Which, as you know, is referred to as the Rayleigh-Jeans limit. So in this limit, this brightness temperature, or this B nu or B lambda, reduces to essentially this relationship, right? 2 kT by lambda squared. And that is the regime in which we are going to be working. This temperature is what radio astronomers or solar radio astronomers refer to as brightness temperature. And as you can guess, this is really the temperature of a black body, which is going to produce the amount of radiation which your telescope has measured. Right? This does not necessarily need to be the physical temperature of the body. In fact, you can check if the radiation which you're receiving is thermal or not by making the observation at different frequencies. And if all of them still return to you the same brightness temperature, that means it must be thermal emission. But if the temperature changes as a function of frequency, it's clearly coming from some non-thermal mechanism. Okay. Now, the units in which people measure this brightness is referred to as Jansky. Jansky was, this is in honor of the scientist who first discovered radio emissions coming from outside the sun, outside the Earth. So 1 Jansky is an enormously tiny amount of energy. It's 10 to the power minus 26 watts per meter square per hertz. And sensitive telescopes now can actually go to millijanskys and even microjanskys. The GMRT, the telescope which my institution runs, the best images we make, they have noise measured in microjanskys. And the fact that these radio telescopes are so sensitive also helps you understand the fact that even though the flux density, even though the energy being emitted at radio wavelengths is so much lower than what is being emitted at EUVs and X-ray and optical, radio telescopes are still able to make very high significance measurements of these really tiny amounts of energy, because in absolute terms, they are much more sensitive than EUV or optical instruments. The sun is the brightest source in the sky, in the radio sky, and the optical sky as well. And so for describing the sun, people use a different unit. It is called unimaginatively solar flux unit, or 1 SFU. And 1 SFU is equal to 10 to the power 4 Jansky, 10,000 Jansky. Now, the sun is an extended source, right, of 32 arc minutes in diameter in optical. And so there is a quantity which is referred to as specific intensity. It is measured in units of Jansky per beam or SFU per beam, where beam refers to the resolution of your instrument, right? So if your resolution is, let's say, an arc minute, you are looking at an arc minute squared area on the sun. And this integral, if you were to do, that would be the specific intensity corresponding to that patch on the sun, right? It's the integral over the brightness temperature over that particular solid angle, which corresponds to the beam of the telescope or the resolution of the telescope. Okay, so the thermal radio emission, and by that I mean the emission from the quiet sun, which is what I have highlighted in this plot. Okay. So if you wanted to understand thermal radio emission, what you need to look at, we need a little bit of basic. You need radiative transfer a little bit to understand what is happening. So imagine there is the chromosphere, right, which is at some 10,000 Kelvin, and it is optically thick, and it is radiating. On top of that is sitting some corona. So let's say this T in corresponds to the temperature which is input on the corona. This medium is essentially the corona, and what is coming out at the other end is what is coming towards us. So now, depending on the properties of this medium, what its optical depth is and what its temperature is, the temperature of the radiation which you see coming out of it will get modified, right? Whatever was input onto this medium will get attenuated by the optical depth corresponding to this medium. And then this medium itself is emitting. And again, the contribution of that will depend on whatever the optical depth of this medium is. And eventually you are going to see some different temperature. The radiation temperature would be different from what was incident on it. And for the case of the corona, under the physical conditions which are relevant here, this optical depth can be is essentially proportional to square of the electron density and has T to the power 3/2 in the denominator, right? And optical depth, like all optical depths, is an integral along the line of sight. So one more thing which one has to keep in mind as one is trying to study the sun, the thermal emission from the sun, is that, you know, you've all heard of coronal electron density models, maybe the Newkirk model or the Saito model and so on. So that tells you that there is a very steep gradient in the electron density in the coronal regions, right? A consequence of that is that the electromagnetic waves at these radio frequencies, few hundred megahertz, they no longer travel in straight lines. Now, these density gradients are large enough that these rays get refracted as they travel in this medium. And this figure shows you what would happen for the case of a Newkirk density model for electromagnetic radiation at 200 megahertz. And so what you notice is that there is this distance of minimum approach. Closer than that, you cannot go to the sun. And I was just telling you that the optical depth which you measure is an integral along this line of sight, and it is weighted by NE squared, right? And if you look at these density models, they have terms like which are proportional to 1 upon r to the power 6 and 1 upon r to the power 16, which means that this density gradient here is very, very steep. Which means that most of the optical depth which any given line of sight will pick up will be actually from this region, which is very close to the point of closest approach of that line of sight to the sun, right? Now you can also imagine that if I had made wideband observations, if I could dial my frequency knob up and down, if I go to higher frequencies, I can penetrate closer to the sun. If I go to lower frequencies, my rays will turn back at higher solar heights. So by changing the frequency of observation, I can essentially sample different coronal heights, right? So you can think of it, at different frequencies being corresponding to different layers of this coronal onion. Right? And this information is really very difficult to get by other means, right? So here we are sampling the region between say 1 and 2 solar radii, which is something which the telescope I work with can do very well. And typically, though we are hoping with Aditya-L1, we will get a coronagraph which will allow us to get closer to the sun. It has usually been quite difficult to observe this region. So this is one of the advantages which radio offers. Another thing which I will return to a bit later in my talk is the second point which is mentioned here, that we also know that this coronal region is magnetized, right? And so that makes this plasma essentially birefringent, which means that even though this thermal radiation, which is originating in the corona, is unpolarized when it is born, as it is propagating through this birefringent medium, it picks up a very small degree of circular polarization, less than 1% at these meter wavelengths, right? And so if you can measure that, that allows you to make a measurement of the average coronal magnetic field. It's always going to be the line of sight component of that magnetic field, but nonetheless, it allows you a measurement of the ambient coronal magnetic field, which we have no other means of measuring right now. Okay? So these are some of the things which you can learn from solar radio observations about the thermal emissions. So this is again making the point which I was making earlier, that there's a sun, the background is actually an image taken during the solar eclipse. And this just shows you the field of view of LASCO, which starts at 2 solar radii. There is another line which at 1.3 solar radii, which is typically the extent of the fields of view of instruments at EUV and X-ray. And the other thing which radio allows you to do is that because it does not need any occulting disk, it can look at the full unobscured disk of the sun, right? So it allows you to study the regions overlapping with EUV and X-ray, and extends well into the coronagraph fields of view and even beyond, as I will show you a bit later. Okay, so now let's also talk a little bit about the non-thermal emissions which you see from the sun. These non-thermal emissions are all associated with solar activity. And that activity, as you know, comes in a very large variety. So there are these short, very well-defined flares or bursts. And there are also these storms, of sometimes also referred to as noise storms, which can last from hours to days. The emission mechanisms which give rise to this, we can broadly classify them into two types. There are the so-called incoherent emission mechanisms. The examples are gyrosynchrotron and gyroresonance. They are essentially the same phenomena. Gyrosynchrotron arises from highly relativistic electrons, while gyroresonance is from mildly relativistic electrons. And so the gyrosynchrotron is important for flares and CMEs where it is possible to produce these highly relativistic electrons. And the brightness temperatures of the emissions from these guys ranges between 10 to the power 4 to 10 to the power 7 Kelvin. The gyroresonance, as the name itself suggests, is a resonance phenomena. So it takes place at multiples of the gyro frequency, so where S is that multiple. And these emissions are often seen on top of active regions. And in fact, this is a very good way of doing what they call magnetography of active regions, where, again, as you scan across frequency, different regions where the magnetic field strength differed, they become opaque at different frequencies. And there again, you can look at multiple layers or multiple heights above that active region as a function of the magnetic field. The other class of active emissions from the sun are what are referred to as coherent emissions. And really the most important class there is the so-called plasma emissions. There is another class of emissions which people have studied here as well. That's called ECME, or electron cyclotron maser emission. But the bulk of these coherent emissions come from the so-called plasma emission mechanisms. So I'll not get into the detail of what these plasma emission mechanisms are, but I'll just highlight for you the sort of variety of emissions which you can see from this emission class and how they are related to a typical flare. So this is a canonical figure where the time t equals 0 is when a flare was launched. It's a little incomplete actually. There should be a bunch of these type 3s before the flare was also launched. But so typically soon after, within minutes of when a flare is launched, you see these type 3-like bursts, which look essentially like vertical lines on a plot like this. They are arising from electron beams which have been accelerated at the site of this flare, and they are now moving along open magnetic field lines in the corona, and are giving rise to these streaks of emission. The other bursts which you would often hear about are the so-called type 2 radio bursts, which are associated with CMEs most often, or with some shock which is propagating in the corona. And it is from the locations of these shocks that these electrons are being accelerated, and as these accelerated electrons are traveling through the corona, they are giving rise to electromagnetic emission at the local plasma frequency and its harmonic. So that is why you see two strands. Type 3s also have emission at the local plasma frequency and harmonic. The other various other things which are mentioned here, they are sort of continuum. They occupy large spans in the electromagnetic spectrum. It's only now that we are beginning to be able to resolve structures inside these type 4s, type 3s, and type 1s. Till now, typically they have been seen, as a diffuse patch of enhanced emission in the spectra, or in the dynamic spectra, right? Intensity as a function of time and frequency. But now with the resolution of the instruments which we have, we are able to see actually structures inside these, and and I'll show you some of these as we go ahead. Okay, so these plasma emissions, like I said, they are coherent emissions, which means that they can have extremely high brightness temperatures, right? The highest which are theoretically possible and also have been measured, they go up to 10 to the power 13 Kelvin. Okay, these emissions tend to be narrowband. They take place at the local plasma frequency and its harmonic. Local plasma frequency, as you know, is proportional to square root of electron density. That means that as soon as I know the frequency of observation of these active emissions, I can already know the the density of the region from where they are born. Okay, and you can take a step further and you say that, well, I know I have a good model for electron density distribution in the corona, and if I make use of that model, then I can also associate a expectation for a height in the corona where this emission must be born, right? So that is one very interesting thing and very useful thing about these coherent emissions or these plasma emissions. And as I just showed you, this emission can have pretty elaborate structure in the time frequency plane, right? So just digging a little bit deeper into these. So in this plot, the frequency is shown on the x-axis, and on the y-axis, there is the height above the solar surface in kilometers and in solar radii. And these regions tell you essentially which emission mechanism is predominant where. So most of my work has been at these lower frequencies, and there, as you see, it is this plasma emission and the Bremsstrahlung and the thermal emission, which is prominent, right? If you were to look at the region which for example, the VELC is going to sample, right? The coronal heights which VELC is supposed to sample, you can figure out what would be the frequency range in which this emission should take place. I should have mentioned that these two lines, one which corresponds to the plasma frequency and the other which corresponds to a height where the medium begins to become opaque to its own radiation, right? Where it's picked up a free optical depth of unity. These are the frequencies where the bulk of the emission would take place. And where the nu p is above nu tau, that's when the emission would be at nu p. Where nu tau is above nu p, then nu tau would be the frequencies where this emission would typically take place. The instrument which I have been using typically observes here, and therefore this is the height range essentially which it is able to examine. And these curves are approximate, and the solar conditions change quite dramatically over as a function of solar cycle and depending on what events are taking place. So essentially you can sample from a fraction of a solar radius to a few solar radii in these frequencies. We've recently started to work with another instrument. Both of these, by the way, are precursors for the square kilometer array, which is going to come online by the time you guys are late into your PhDs, around 2027 or so. So with this, we are expecting to now, probe the chromospheric regions, while all of this is probing the coronal regions. So just a word or two about the emission mechanisms, which I already talked about. So gyroresonance, thermal electrons gyrating in the coronal magnetic field, gyrosynchrotron, non-thermal electrons doing the same thing. Bremsstrahlung, that's the free electrons interacting with ions and other scattering centers. Plasma emissions, they tell you about the growth rate of these Langmuir waves, which is a nonlinear phenomena. And you also occasionally see this ECME emission, which is again a nonlinear growth of plasma waves at the harmonics of the electron cyclotron frequency in the plasma. Okay, so what sorts of instruments do we use to study the sun? So essentially we use two kinds of instruments. You could call them spectrometers, which sort of you could say is studying the sun as a star. These are single dishes, and they give you integrated solar flux density as a function of time and frequency, right? So they can't tell you about the location or the morphology of the emission. So you're treating the sun as a star, and you're looking at the emission from the sun and how it is changing as a function of time and frequency. And a lot of what we have learned about the sun actually comes from the studies of the dynamic spectra from these spectrographs. Then the other class of instruments is what is referred to as interferometers, right? These are the guys who are able to make images of the sun. And now we have the capability to make to do full polarimetry with these instruments. So not only we can make images, with pretty fine time resolution, pretty fine spectral resolution, and full Stokes. So you essentially get something like a 5-dimensional data cube. I'm sorry, I don't know why this font is so poor here. So you have your intensity, which is naturally a function of the 2 dimensions of the image, right? And because I'm making an image every time slice, I have a time index here. Similarly, I can make images over very fine spectral resolution. So I have a frequency index, and this S represents the Stokes parameter. So I can make an image for the intensity, the two linearly polarized components Q and U, and the circularly polarized component of emission V. Okay. Okay. So what is the nature of this solar radio emission which we want to study? So just to quickly give you a sense for that. So the time scales of variability, they range from milliseconds to solar cycles. So the implication of that is that you really want an instrument which is capable of giving you high time resolution observations, and you want observational programs which allow you to observe the sun for an extended duration, right? If you want to capture this full scale of variability which you see. Now, across the frequency, again, the range of variability is quite high. On the one hand, you have this very smooth black body-like spectrum, which is very smooth across hundreds of megahertz. And then you have these active emissions, which can vary over spectral scales, even less than 100 kilohertz. So then the observing demand it places on you is that you want an instrument which is capable of observing over a very broad spectral band, but with very fine spectral resolution. How about the angular scales at which this emission is present? Well, as you will see in a few examples, that this angular scale can vary from a few degrees to less than a few arc seconds, essentially to the resolving power of these instruments. So again, okay, we have not yet talked about how interferometry works, but just take it on faith for now that the requirement it imposes is that the baselines of my interferometer, right? That is the separation between the individual elements of my interferometer must span a very large range, from very small, which will give me this large angular resolution, to very long, which will give me this fine angular resolution. In terms of brightness temperature, I've already mentioned that, for example, gyro synchrotron gives emission which can be even less than 10 to the power 4 Kelvin, and bright type 3 bursts can go to 10 to the power 13 Kelvin, and sometimes these guys would be present together. So you really want an instrument which is capable of very high imaging dynamic range, right? And a lot of the radio emission is polarized, and the most interesting aspect about that is that polarization, more often than not, is carrying information about the magnetic field in the environment where that radiation was born. And that magnetic field is very hard to get a handle on by any other means, right? So it's very interesting to do this, to study the polarization. And the requirement that imposes is that you really need to do full Stokes imaging, right? Polarimetry. Okay, so now looking at some data, some real data to see what the radio sun actually looks like. So on the x-axis here is frequency, and there are actually 12 chunks. Each of these chunks is 2.5 megahertz, and it is the central frequency is what has been mentioned here, right? So they go from 80 to 300 megahertz roughly. On the y-axis is time. The time resolution is half a second. Total data span is about 5 minutes. And these are data from a telescope called the MWA. And the very nice thing about this telescope is that for every pixel on this plot, I can actually make an image. So if I was to actually do that, I'll end up with almost 500,000 images in just 5 minutes. And about the emission, what I want to point out is look at the detail of features in here. There are things which are, for example, they occur in this 116 megahertz band, but there is no trace of them around 100 megahertz or around 120 megahertz. You can already see that this emission is sort of fainter here and brighter at this end. These vertical lines, by the way, are instrumental artifacts, so you can ignore them. And these are sort of thin fibers of emission, right? They're very short-lived in time. All of these emissions are actually non-thermal emissions, because the thermal emission, by definition, will have to be smooth across frequency, and it is impossible to heat or cool a large amount of plasma, over a fraction of a second. So it's also going to be varying much more slowly in time. So in fact, this instrument sort of helped us realize for the first time how much of this weak non-thermal emission is present on the sun. Okay, so the thing I want you to keep in mind is that it is the details of this emission which we really want to image when we want to go after solar imaging. So basically things which are changing very rapidly in time and very rapidly in frequency. Okay, the other aspect of the challenge which I want to highlight is what is shown here. So the red boxes correspond to the y-axis on the left, and they talk about the brightness temperature of the emission, and the blue boxes are the fractional circular polarization, which correspond to the y-axis on the right. So they are arranged roughly in the brightness temperature order, peak brightness temperature order, which goes from, this is an older version. This should have been 10 to the power 13 here. And they go down to something like 10 to the power 4 for the gyrosynchrotron emission from CMEs. The quiet sun emission is at about 10 to the power 5 to 10 to the power 6 Kelvin. And the fractional polarization of this signal can range from, close to 0 to 100%. For the quiet sun, it's less than 1%. For type 4s and type 1s, it can be as high as 100%. These sort of boxes at the bottom, the first 4 of them show you what these emissions would look like in the dynamic spectrum. Right? This is just an image of the quiet sun, and this I'll talk about later as we go along. Okay, just a couple of slides about radio interferometry. So it's a sort of fairly involved subject, but I want to give you just one slide introduction to how radio interferometry basically works. So let's start with a very familiar situation. So you're all familiar with a parabolic dish, and the beautiful property of a parabolic dish is that no matter where you are starting from on this wavefront Q1, Q2, or Q3, by the time you arrive at this focal point, the path length which you have traveled, right, from Q1 to where you hit the mirror and from where you get reflected from the mirror to the focus, they're all exactly identical, right? So they arrive at the focus in phase. Now, imagine that I remove some parts of this mirror, and that is the picture at the bottom. So even if I was to remove some parts of this mirror, the parts of the mirror which will remain, they will still retain the property that the light will still come to focus in phase, right here. Now take the next step and say that these pieces of mirrors, I'm going to move, but I'm going to keep very precise track of exactly where I have moved them. So I'm going to move them to various other places and measure the locations where I have moved them so that I can delay their signal appropriately and make sure that I can still add all of the signal in phase. Right? It's possible to do that here. And that really is what an interferometer is also doing. These pieces of this mirror, they become the individual telescopes. Interferometer works typically in sort of units of baselines where it is going to do pairwise combination of the signals received at individual antennas. And that really corresponds to one Fourier component of what is there in the sky. And different baselines measure different Fourier components. And finally, you put them all together and do an inverse Fourier transform to get an image of what is there in the sky. There's a lot of detail about how you calibrate and details of the imaging process and so on and so forth. But conceptually, this is what is happening. And that's really what I want you to know. Okay. And just like, a soft X-ray instrument is very different from an EUV instrument, it's different from an optical instrument. The radio telescopes will also vary quite dramatically across this frequency range, right? So here I'm sort of showing you 3 examples from the highest frequencies at about 1,000 gigahertz to lowest frequencies which I work with, which are about 100 megahertz, right? So 10 to the power of 4 variation across the wavelength. So these guys, this is ALMA, which is located, at more than half the height of the Everest in the Atacama Desert in Chile. These dishes are ultra smooth because their surface accuracy has to be, at least a 20th of the shortest wavelength they are working at. This is the GMRT, which is located just 80 kilometers from where I'm sitting today. And here you can see that the reflecting surface of the dish is actually transparent. It's actually a wire mesh, which is 1 centimeter by 1 centimeter in size. And we can get away with that because the wavelengths which we are working with are much larger, right? From about 2 meters to about 20 centimeters. This is the telescope from where I'll be showing you a bunch of different examples. This is the Murchison Wide Field Array, where we don't have a dish at all. Where all we have on the ground is actually a 4x4 array of cross dipoles. And the signal from each of these is combined to to make a beam on the sky, and that becomes your telescope, right? And one interesting fact about this particular place is the very low population density. It is about the size of Netherlands, and it has less than 20 people living there. So the population density is something like 3 millihumans per square kilometer. Okay, so now I've convinced you that if you really want to do good imaging of the sun, you must gather the information which you need over very small temporal spans and very small spectral spans, right? Which means that all the Fourier components of this image which you want to make, you must gather essentially instantaneously and in a single spectral slice. And that is something which this MWA is extremely good at, right? So these three figures, they are sort of successive zoom-ins, and they show you the density of the coverage in the Fourier plane, right? It is the components, the brightnesses which would be measured for these Fourier components, which would be inverted to give rise to the image which you see. And till now, or till the time the SKA comes along, this is going to remain actually the densest Fourier coverage which you are going to get for sun-like systems. And so this is really right now among the best instruments, or maybe even the best instrument in its frequency range to be studying the sun, right? So another thing which you need is that if you are going to be making an image every time slice and every frequency slice, you are going to end up with a very large number of images. So that you cannot sit and make individually by hand. You must develop a pipeline which will allow you to do it, in a robust and unsupervised manner. And that's something which we have been working on. And here are some examples from the first pipeline which we made, which very creatively was called Air Cars. So on the left, you have an image which was taken when a type 2 burst was in progress. The yellow dashed line is the optical disk of the sun. You can see that the radio disk is much larger. The type 2 is taking place here. And the dynamic range of this image, which is essentially the contrast between the brightest features and the noise, is larger than 10 to the power 5. And on the right side is the sort of featureless radio disk at frequency of about 240 megahertz. Here again, you can see that the radio disk is significantly larger than the optical disk. And as I should have pointed out, the highest brightness temperature here is about 10 to the power 9 Kelvin, right? 10 times 10 to the power 8. While on this one, it is just about 4 times 10 to the power 5, right? So about 4 orders of magnitude in difference in the brightness temperatures, which you're able to see here. And as it turns out, because of reasons I don't want to get into, this imaging the quiet sun is much harder than imaging the active sun, where you have a nice bright point source. And even here, we are able to get imaging dynamic ranges of order 1,000 or more. So the thing I want you to sort of take away is that we already have good, robust implementations of pipelines. The images, the dynamic ranges which I'm talking about are sort of 2 to 3 orders of magnitude better than what earlier instruments have been able to do. So naturally, they are now the state of the art. And naturally, when you are going to be looking at things in such detail, you are going to find a large number of interesting and beautiful things. Now, not only that, we have also now more recently built the ability to do polarimetry with these images, right? Like I was telling you that polarization carries information about the magnetic field. That's really very interesting. Okay, so this is a type 1 solar radio burst. Never mind what a type 1 really means. All I want you to notice is that these green contours, they correspond to the Stokes I, or total intensity, and the colors tell you the percentage circular polarization, and you can see that it is sort of going up to minus 70% or so circular polarization. Similarly, this is a different example taken from type 2. Now, another thing I wanted to point out here is not only we are able to see circular polarization, we are also able to see some linear polarization from these active emissions. Now, conventional wisdom has been that this linear polarization should actually not be seen, because if this linear polarization was born at the same place where this burst emission was born, it has passed through so much magnetized coronal plasma that because of Faraday rotation, it must be actually all depolarized. But we are finding robust evidence for its presence. And this is something which I'll come to later again, this is that for the first time, we are detecting circularly polarized emission from the white sun regions as well. That is very interesting. Okay. So what we've managed to do here is that we've managed to build polarization, ability to do polarimetric imaging, which is comparable with the best which is possible, even when looking at nighttime sources. And now this allows you to do, an exploration of truly unexplored phase space. And that is what I find very interesting about it. And I'm now going to give you just a few examples of some of these explorations which we have done. Okay. So I mentioned that one of the things we realized very early on was that there is a lot of weak non-thermal emission coming from the sun. And sort of that became one of the focus areas of our research. But why is it interesting to study these weak emissions? I'm sorry, these arrows have gotten displaced from where they were supposed to be. Okay, so these weak impulsive non-thermal emissions, they are believed to arise because of weak magnetic reconnection events. These are the same magnetic reconnection, the same class of magnetic reconnection events, which we have studied in context of flares and so on, but they are happening at much, much lower energetics, right? So these magnetic reconnections, they give rise to local plasma acceleration. These local plasma acceleration, that energetic plasma is confined into an electron beam because of the overlying magnetic field. And then as this beam is propagating through the corona, it is giving rise to plasma emission at its plasma frequency or the harmonic. Now, recall that this nanoflare-based coronal heating has been proposed and is really one of the most promising explanations for coronal heating. A lot of effort has been put in looking for evidence for that. And most of that has been at X-rays and UVs, where people have been looking for thermal signatures for presence of these nanoflares. And okay. So we are now able to detect these nanoflares, but the characteristics of the nanoflares which have been detected so far, they are not compatible with what is needed to explain coronal heating, right? So there are two things which these nanoflares, the two characteristics which these nanoflares must have. One of them is that the power law index of their distribution should have been steeper than -2. And we have firm measurements which place the power law of all the nanoflares which have been detected at -1.8 with very low uncertainty on that. And the other feature is that these guys should be ubiquitous on the quiet sun. And the problem there is that the nanoflares for which we have imaging information, all of them tend to lie in the vicinity of active regions, or they mimic the distribution of active regions, and which, as you know, never exceed, plus minus 35 degrees north or south. But even the coronal poles are hot. The corona even there is hot. The chromosphere even there is 10,000 Kelvin. So you need something which is happening all over the sun, not just in the vicinity of the active regions. Okay. Now, the radio emissions which we are looking at, these, like I said earlier, are arising from coherent emission processes, while the X-rays and EUVs are thermal. Now, the coherent nature implies that even for energetically small events, the observational signature which you can see, the brightness temperature which that thing would give rise to can be quite large, right? And so it is very interesting to look for evidence for these guys. In the radio frequencies. It's hard work because now you want, you're looking for something weak, which is going to be very short-lived in time and which is going to be very narrow band. So that makes it hard for a Fourier imaging instrument to look at. Nonetheless, people have been looking at these, and naturally you start with active regions when you're looking at this. Is in fact work from the IAA group. And you notice the title says picoflare, right? Low frequency radio observations of picoflare category energy releases. So even though these were coming from actually a type 1 noise storm, and these are quite bright by our standards now. So their flux densities are 1 and more, right? Let's say 1 to 10 solar flux units. But these were still much weaker than the nanoflares which had been detected at EUV and X-ray. And if you were to associate an energy with them, they would be lying in the picoflare category, right? Okay. Now we tried to do something similar with the MWA, and this is a dynamic spectrum where we again look at a type 1 storm, and each of these green dots is supposed to be the location of emission feature, which was identified by a wavelet-based algorithm. On the right panel is really the same as the left panel, except that the color scale has been saturated at about this level, at 10 SFU. And so that shows you that even some of these things where you were wondering why is this green dot here, now you begin to see that there are faint features which are associated with that here. So what we learned from here, just give me a sec, is that, you know, in this particular really weak storm, we've identified, you know, thousands of such events every hour, even during these fairly weak storms. And the strength of these was comparable to the weakest features which had been reported till that time. That's about an SFU. And very interestingly, we found their spectral index to be steeper than 2. Which was quite interesting at that point. So that sort of got us started on our quest for looking for weaker and weaker features. This is a slightly more advanced technique, which is now trying to decompose what you are seeing in that frequency time plane into a bunch of Gaussian components. And the idea is that if it is a quiet time, then the dominant component is going to be the quiet sun, and all the active features are going to be these Gaussians with higher means. And you could see that the model, which is this orange line, is actually reproduced the data, which is the black dots, quite well. So what we learned from there was that, you know, our general expectation is that impulsive features, weak active emissions are, you know, their strength is much lower than the quiet sun, but that was not the case. So here, this green line and green data, that tells you the strength of the slowly varying component. And these blue lines tell you the strength of the impulsively varying component, right? And they seem to be quite similar in strength, which was quite a surprise for us because this was not an active time during which these data were taken. This is showing the same thing in a different way. So let me just move on to the key takeaways, which is that even during moderately quiet times, there is a lot of impulsive emission which is taking place. In fact, 20 to 50% of the emission can be impulsive. And now we were able to get down another order of magnitude weaker to these non-thermal elements. All those things which I was talking to you about, they came from non-imaging observations. And once we built our imaging pipeline, we were able to look for these in the images. And this figure on the left, it shows you essentially the occupancy, the fractional time occupancy of the presence of such features on the disk of the sun, right? And you will see it rises up to about 10% or so here. And they're present all over the sun, right? Which is what you really need for them to be relevant for coronal heating. The right panels, this shows the intensity distribution of these guys. Now that you see looks nothing like a power law, which I was talking about and which I said must have a slope steeper than -2. But what we can show is that there are so many of these events happening that they are sort of overlapping with each other and our observations are not able to resolve them. And in fact, some prior work had shown that in such a case, what you will end up with is something called a log normal distribution. And that is what is seen here in these plots. These red lines are actually log normal fits to these data. And now we are able to get down to few milli SFUs, right? So we've gone sort of 4 orders of magnitude from what other people had done, from about 10 SFU to about a milli SFU, or at least 3 orders of magnitude. And these are the first direct detection of what we now call weak, impulsive, narrowband, quiet sun emissions, or WINCs. And it's really heartening to see that they are taking place all over the sun, which is what you really need for them to be relevant for coronal heating. Then, okay, I think I'm a bit short on time, so I will skip through this, but this was going to talk about what are the shapes of these guys. And this, this maybe I can say something about, you know, whenever you are operating close to the limit of any instrument, you have to be really careful in the work which you are doing. So what we wanted to do is to also develop an alternative technique using which we could develop, detect these WINCs. And that is what this thing talks about. In the image plane, they still look like these very compact features. If you look where they are taking place on the sun, these are the distributions. And these are really the sweet spot of performance of our telescope, really above 150 megahertz or so. And you see that they are distributed all over the sun. if you look at how bright these guys were, these is in units of kilokelvin, you find that most of them are sitting somewhere here, right? Somewhere between 5, 6, 7 kilokelvin are the brightness temperatures. Remember that the quiet sun itself is 1,000,000 Kelvin, right? So these are sort of less than a percent of the brightness temperature of the quiet sun. So that is what really makes it hard to study. Okay, I told you that even though the thermal emission which is born is unpolarized in nature, but as it is passing through this polar magnetized corona, this birefringent corona, the radiation splits into X mode and O mode, and it picks up a weak circular polarization. So this has in fact been a subject of intense study, and the top figure that comes from some work by the Gauri-Bidnoor group, and it shows the B they have estimated for the time of a CME. So there are 3 panels on top. This Gauri-Bidnoor instrument is a transit instrument. So these are observations on 3 successive days. And in the middle day, there was a CME which was happening to pass through their field of view during their observations. And this green line is telling you the measurements in Stokes V, and the blue line is, or blue data is the measurements in Stokes I. So there was no Stokes V present on the other 2 days, but the day when the CME was present, there's a significant signature of Stokes V. And by measuring this degree of circular polarization, they estimated the magnetic field to be at about half a Gauss at a height of about 2.1 solar radius. Right? This is not an imaging observation. This is just sun as a star observation. We now have actually the first measurement of Stokes V from the quiet sun, which is what I'm trying to show in this image. So this is, or maybe it's better to look at this image. So this is the green contours are Stokes I, and the color is circular polarization. And it is this region right here, which is the quiet sun part. And we have a high significance detection here. We measure more than 0.5% of polarization in this image at 96 megahertz, and our noise is only 0.07%. Right? So it's pretty good. And using a comparatively simple and somewhat naive coronal propagation model, we estimate the magnetic field to be about 350 milligauss at about 2 solar radii. Right? This is really the first measurement of coronal magnetic field. Okay, direct from observations here in the radio. Okay, so another thing which these radio observations are very good at are about their ability to constrain coronal turbulence. So what you see on the left panel is actually something called a type 3B burst. It doesn't matter why the name is whatever it is. But what I want you to focus on is the large variation in intensity which you are seeing here. A cut across that is what is shown in the right panel. And you'll notice that all of these are actually high SNR measurements. The noise on this signal is, at this level. So when you are seeing all these fluctuations, all of these are real. Okay, they are not noise. So what this allows you to do, again, without going into the detail, is that this allows you to estimate the level of inhomogeneity in the medium, or what is referred to here as delta Ne by Ne. And in fact, this work, which was again by the Gauri-Bidnoor group, it shows that if you were to compute a spectrum of delta Ne by Ne whole squared here, it shows a Kolmogorov-like slope, which basically means that this turbulence is well developed. And so that's again, and these are all aspects which you actually cannot get a handle on from any other wavelength. Because this microphysics, you really need these radio observations to get a sense for. Another example, this time from imaging observations on a different telescope, LOFAR, is what is shown here. So this is again a type 3B burst, and a zoomed in view of this is shown here, which just shows in real exquisite detail the variability seen here. And for one of the data points here, this is the image, right? So this red circle is at one frequency, the blue circle is at a somewhat different frequency. This ellipse shows you the point spread function of these observations. And you find that even though we know that this emission must arise from a compact source, in our images, it looks much larger than our resolution element or point spread function. And that is happening because of the propagation effects, because of scattering and so on. And so what these guys had managed to do, that they were able to make an image every 50 milliseconds and use that to investigate the radio propagation timescales in the corona, right? And they showed conclusively that it is actually these propagation effects which dominate the observed morphology of the radio burst and not the intrinsic properties of the emission itself. We had also attempted to do something very similar. And if you were to look at this left plot, it is essentially showing you how the area of, in this case, a type 3 source is increasing as a function of time. And what I want you to think of is that imagine I switch on a source in a turbulent medium and you are sitting far away and observing. The earliest light to reach you would be the light which would have traveled essentially in a straight line. And for the things which have been scattered more and more and taking longer and longer random paths, they will take longer and longer time to reach you. But because these things have traveled through longer random paths, they would also appear to be coming from further away from where the radiation was born, right? So the area of the source would seem to grow as a function of time. And if you can measure and model that, you can estimate the level of electron density in homogeneity in that medium. So that is exactly what we did in this work. And this is an estimate of how this area is growing as a function of time. You can invert that to get that this delta n by n is order 1% at these coronal heights. And this also established that the level of inhomogeneity we have and the nature of scattering which we see is already in the so-called strong scattering region. Right? So what the implication of that is that the source does not keep growing, the source size does not keep growing. It grows to some extent and then saturates beyond that. Okay. Let's look at a different kind of burst. This figure is just to demonstrate how the new data is so much better than the older technology. So this is a Kalgura spectrograph, which has been in operation for decades. And on the right, you see a zoom in of just this piece, right? And you can see really the exquisite detail in which we can see this variability here. Now, these are type 3 radio bursts. And like I said, these are electron beams which are traveling along open magnetic lines of force. Keep that picture in mind. So the top left, or either one actually, let's look at the top right, in fact. So the blue curve shows you the integrated flux density and the red curve shows you the area. And what you will notice in this plot is that there is some sort of a quasi-periodic oscillations in both of these quantities. And wherever there is a valley in blue, there is a peak in red, right? And that shows you that there is sort of this anti-phased oscillation which is taking place in this type 3 burst. And that is also visible if you were to do a cross correlation of these guys. This is the cross correlation between the integrated flux density and the area, and that you see a dip close to 0, quite a significant one. And what this is telling you essentially is that there is naturally something which is modulating the size of this beam. And whenever it is brighter, it is more compact. And as it grows in area, it becomes fainter. We ruled out that something like this could arise because of an MHT-like process, because the speed with which these oscillations seem to be traveling, that exceeds 100 times the expectation for the alpha speed at these coronal heights. And so this implies that whatever is giving rise to this modulation is actually happening at the site of this particle injection or acceleration into this open magnetic field line. Again, a sort of result which this level of detail in what is happening, you are not able to get access to via higher frequencies, okay? Optical or X-ray or EUV. Okay, this canonical picture, I'm sure you've probably seen many times by now, right? Here is some magnetic reconnection which is taking place from where electrons are proceeding both downwards and upwards. The guys which are going upwards, we are going to see in radio. The ones which are coming down, where they hit the photosphere, you are going to see the hard X-ray, right? And these observations show exactly that. So the background is an EUV SDO 131 angstrom image. This is the hard X-ray, and these are the locations of the radio centroids, where the reds correspond to the highest frequency and therefore the lowest heights, and the blues correspond to the lowest frequencies and therefore the largest coronal heights. And if you were to slice it in time, these are every 100 milliseconds. So you can see these beams rise as they go out and shift from higher to lower frequencies. This is just another example of that. So really, you can see a lot of detail in the propagation of these electron beams if you have the right sort of data. Okay. And these guys also found, in this particular instance, they found the delta NE by NE to be much larger, almost 25%. Okay. So, Vaibhav, are you there? Yeah. Yeah. So I just wanted to check how much time do I have? Can I take another maybe 15 minutes or so? Yeah.
You can take more. I'm Krishna here. Vaibhav is not here.
Yeah.
Divya. Okay.
Sure. Okay. Thanks, Krishna. Yeah. Okay. So let's talk about a different kind of burst, which I introduced briefly earlier, which is called a type 2 burst, which I said is typically associated with CMEs or shocks, right? And this is again emission taking place at the local plasma frequency, or it's harmonic. It's just that the electron beams which are giving rise to it, they are being accelerated at this shock front. And this emission is often split into, both the fundamental and the harmonic emission are often split into multiple bands, usually only two, but with higher sensitivity observations, we are able to see multiple bands. And that is what you are seeing here, right? You can imagine sort of a band here. Maybe this is another band. This is a third band. So maybe a fourth band. There is weak suggestion of another band here, right? So what a telescope like the MWA allows you to do is that, like I said, for every pixel on this map, I can make every pixel on this image, I can make a map. And so for each of the circles which I've plotted here, I actually made a map. And when I did that, this is sort of what I saw. If I make a map from taking a pixel from a region where this type 2 emission is not active, I see something like this, right? And in some arbitrary units, the peak flux density here is 0.04. When I go to a region, maybe somewhere here, I see still at the same location, I see a very bright source, which is now maybe something like 100 times brighter than the source which I saw here. And it has now become so much brighter that I can no longer see the quiet sun. And if I identify the place where the peak, which corresponds to the peak of the flux density seen in this plot, I find another source at the same place, looks pretty much the same, except that it is now 10 times brighter. So I have sort of 4 orders of magnitude of difference in the peak brightness between here and here. But I invariably find a point source everywhere in this, and that I know is the source from where the type 2 emission is coming. So what I did next is I just looked at how is this point source moving across this frequency time plane. So now what these arrows show is that if I was to plot the location of that point source with respect to some reference position, how has that point source shifted with respect to its location at some particular frequency and time? And in fact, that reference frequency and time is here. The arrow shows me the direction in which it has moved, and the length of the arrow shows me the amount by which it has moved, or it's proportional to that. And you see, very coherent patterns, right? This is not noise. This is very systematic movement in how this point source is moving from across time and frequency. So what this is telling us really is that this correlation length scale across the time and frequency axis, they carry information about the dynamics and the turbulence scales in the medium. So we are in the process of developing actually the appropriate modeling framework to be able to associate these, the magnitudes of these correlation lengths with properties of this medium. Okay. Now, the last example, I think, or actually one before last, which I wanted to give you, is about modeling the gyrosynchrotron emission from the coronal mass ejection, right? Now, they've been expected for a long time. And in fact, this, what you have on the screen was the discovery, or was the first observational evidence, or first observation to measure and model this gyrosynchrotron emission from a CME, right? As you can see, the sort of this bubble reminds you pretty much of what a CME would look like. And they measured the spectra at 4 different places, and you can see them here. The spectral coverage is somewhat poor, but they did try to fit these spectra with a thin, optically thin gyrosynchrotron model, and they came up with magnetic fields of, where am I going? Okay, I can't read it beneath this. The magnetic field strengths are of the order of 5 to 7 Gauss. That's what they had estimated in these regions. Okay. Now, this was in 2001. Since then, we are able to do a whole lot better. So this is some of our work from a few years ago, where again, now we can see the structure and the background, you can see the white light CME. And these are the spectra which we can extract from various regions. So the regions which are being shown here are all in this region. And now we have much better spectral sampling, and we are able to model the gyrosynchrotron emission quite well. And we are also able to do it at much higher coronal or heliospheric heights. In this case, we are sitting at about 2.7 solar radii, and we can estimate magnetic fields of some 7 to 11 Gauss or so. So when we did this at that time, these were the deepest observations and detection at the largest heliospheric distances. One of the interesting things these guys showed is that the filling factor of these non-thermal electrons was very small, just of order 1% of the volume which you are modeling. This is an area in which we have been working quite a bit. This is another example, and actually the figure on the right shows you all the published literature about this work. So the green and the magenta come from our work. Everything else is what's been published by other authors here. So since 2001, and let's say almost 22 years, there have been only so many detections and modelings of this. And that's because this is, like I was mentioning earlier, this emission is sitting at about 10 to the power 4 Kelvin, while this is sitting at about 10 to the power 6. And sometimes there is also a type 2 or something going on when you are looking at these. So it's really hard to measure that. But what we have been managing to do is that in every single CME we have looked at, we have detected this gyrosynchrotron emission, and we are getting better and better at modeling that. We've now, okay. So because we are now able to routinely detect these emissions, we think we are getting closer and closer to using it as a tool for routinely characterizing the CME magnetic fields. Now, very recently, we have also made our first detection of Stokes V emission from the gyrosynchrotron models. Stokes V from these CME gyrosynchrotron emissions. Now, the nice thing about that is that it allows you to break some degeneracy between some of the model parameters. And that's what I'm trying to show here, that this is a sort of MCMC corner plot, which shows you the phase space in which you believe the quantity which you are trying to model lies, right? The various properties which we are looking at here are there's a electron density, the energetic electron density distribution, which is modeled as a power law. This is the minimum of that. This is the theta, which is the angle between the line of sight and the magnetic field. This is the area of the region which you are modeling. This is the delta of this power law index, and so on. And somewhere there should have been the magnetic field here. So if you were to use the Stokes I data only, you would get these blue regions. If you were to use both Stokes I and V together, the parameter space available to you shrinks into the red region, right? So especially the B and theta, we are able to constrain much better than what you are able to do with Stokes I alone. So that's a very interesting development to make use of. Okay. So I'm sure you've heard a lot about space weather already, right? And so the ability to predict space weather is becoming increasingly important now, right? We have many assets in space. We rely ourselves on, Google Maps and so on and so forth. And you also know that the geo-effectiveness of a CME depends crucially on the magnetic field, right? And also that this magnetic field, this vector magnetic field, is very, very hard to measure. Right now, we don't have a good measurement technique. We rely purely on modeling. As far as measurements are concerned, our best information comes really from the satellites which are sitting at L1, which give you in situ measurements. But these fast CMEs are traveling at more than 1,000 kilometers per second. So that gives you only half an hour of advance warning by the time the CME actually hits the magnetosphere. So the only possibility which we have for getting this information about the vector magnetic field of these CMEs, while the CME is still quite far away from the Earth, is via radio observations. How? We can do that via Faraday rotation. This is just to remind you, what is Faraday rotation? That when a linearly polarized light is traversing magnetized plasma, its plane of Faraday rotation is going to change, and by how much it is going to change is given by this. Right? It's essentially any B dot ds, where B is B dot ds. ds is the line of sight, so this is the line of sight component of the magnetic field. Right? So that is what we really want to achieve. So imagine a situation where this is your sun, this is sort of your Parker spiral of magnetic field, and you have this distant source, radio background source somewhere, which is giving out some linearly polarized light. That light, as it is passing through this plasma, it's picking up some Faraday rotation, and that Faraday rotation, if in case there is a CME, that Faraday rotation would be different, and that is what you want to measure. And so if you can do that for a very large number of Pierce points through the CME, then you can try to constrain the 3D model of the CME. Correct? And that is really what we want to do. Now, on the right, what I show you is a real map. This map is enormous in its field of view. It's 60 degrees by 60 degrees. And each of these dots here is actually a true background radio source. The sun was inside this red circle and actually has been subtracted. So this is a little bit like seeing stars in the day. Right? Even though the sun is so bright that one is usually not able to see any source in its vicinity, if you do a very good job of calibration and imaging, then you can subtract the contribution of the sun and begin to see the background sources which are there. If we are able to also measure the Faraday rotation corresponding to the polarized component of emission from these sources, and imagine this was the CME which was going in this direction, for all the sources shining through which are giving out polarized emission, if I can measure the Faraday rotation, if I can do this as a function of time, then I should be able to constrain the model, a three-dimensional model of CME, right? Which typically has these days order 10 parameters. So we are working towards doing a proof of principle measurement for this, essentially measuring the Faraday rotation towards any background source, whether or not there is a CME passing through. And if we can do that, we should certainly be able to do that when a CME is passing through. And the final objective which we want to move towards is really be able to do this in sort of near real time. Right? That's the only way when a prediction is useful. Okay. And towards that objective, one of the things you want to do is you want to make these observations at much higher frequencies than what we have been working at. And only yesterday we submitted this to the archive. These are the first images, solar images from Meerkat. So on the left is a simulated image, and on the right is the image which has been made from the data. So the correspondence between them is quite evident, and some of the bright regions we have marked here so that it becomes easier for the eye to see the correspondence between these two images. Okay. Now, what are the challenges in doing all of these? So challenges essentially lie on the sort of data handling and computation front, and also on the algorithmic side. So our data volumes are enormous. This telescope MWA produces more than a terabyte an hour if we work in the full time and frequency resolution. It is going to change by a factor of 16, increase by a factor of 16 as it goes to the next phase of this development. We already have about 3 petabytes of data in the archive, of which we have looked at maybe 3% of the data. On a pretty decent machine, 36-core machine, it takes me about 12 days to analyze 4 minutes of data. Even after data reduction, my data volume doesn't go down in size. It is still about a terabyte an hour. My data is sitting in Australia, and just getting it here to NCRA, to the machine where I work on it, it is a challenge. And the next set of challenges is that, okay, computational capacity will grow in time, bandwidths will grow in time. So I'll be able to make these hundreds of thousands or millions of these images how am I ever going to extract information from these images? I can't be sitting and looking at them one by one, right? So we need to develop some sort of machine learning or kind of algorithms which would be able to extract information from these very large number of images and present it to us in a form which human brain can make sense of, right? And I did not highlight here the challenges about on the algorithmic front because that requires a more technical background. Yeah, this overlaps essentially with what I was just saying, that this is a kind of new regime which we are entering. So where we need to really look at sort of different and creative ways of capturing this information which we can now understand. So this is an example here. This is actually a stack of images. The z-axis here is the frequency axis. And just this visualization has been done to see how the image is changing as a function of frequency as you go from bottom to up. Okay. And we are now probing really pristine phase space in terms of solar radio physics. And the sun has never, it has never happened that any new instrument which does much better than the previous one has not found surprises. So we are also expecting to find many more surprises. We are already finding some reasonable share of our surprises. For example, I mentioned the linear polarization. So I think it's going to get really interesting as we go ahead. And there's an enormous number of new telescopes which are coming up or are already available. We have the MWA, LOFAR, Jansky VLA, UGMRT, MEERKAT, we are hoping will become available for solar observations in 24. Goribidnor is being upgraded. The SK1 will commence operations in 27. So all of these, in addition to all the data which we are getting from Solar Dynamics Observatory, Parker Solar Probe, Solar Orbiter, we will soon have Aditya-L1 up in space. So I think we are currently not limited so much by data, but by our ability to analyze and interpret it. And that is where I think the intellectual effort and the young people come in. So we are, like I said, vast and completely unexplored areas of phase space are becoming accessible, which means essentially that exciting things will happen in solar radio physics in the times to come. And with that, yeah, okay, I have just one more slide. These are some resources if you want to learn more about it. The second set is about radio astronomy itself. The first set is about physics of the corona and solar radio physics. And with that, I'll stop and take any questions if we have.
Thank you very much, Professor Divya. Let's thank Professor Divya. Okay, now we can take questions.
So when we talked about incoherent emissions, you told us that there are gyrosynchrotron emission and gyroresonance emissions. I wanted to know why we call gyrosynchrotron emission as gyrosynchrotron emissions.
So that name borrows from an emission mechanism called synchrotron emission. Synchrotron emission arises because of highly relativistic electrons gyrating around magnetic fields. And just to distinguish between highly relativistic and not so relativistic electrons, gyrosynchrotron was, the name gyrosynchrotron was given to distinguish from synchrotron. Gyro because, because it is gyrating in the magnetic field.
Then you talked about thermal and non-thermal electrons. How do we know if an emission is thermal or non-thermal?
That's a very good question. So the thermal emission naturally implies that its emission would be black body-like, right? It would follow the Planckian only if the optical depth was infinity. But apart from that, its spectrum should follow the characteristics of an optically thin or optically thick black body, whatever the optical depth of that thing is. So that is your primary metric. If you are able to somehow get the spectrum of that thing, that emission, then you can say for sure if it is consistent with being thermal or non-thermal. Then there are some other things that, for example, if my emission is very narrow band, if it is like a spike in the frequency plane, and I think I'll have some examples here. No thermal emission. So for example, if I have emission like this, right? This is frequency on this axis. No thermal emission process can give rise to a spectrum like that. So by definition, therefore, it will have to be a non-thermal emission. Another diagnostic you have is things which vary quite rapidly in time. If that is arising from thermal emission, that means the plasma has to be heated and cooled at that time scale, right? Sometimes it's possible, but sometimes it is not possible. So if you have extremely rapid variability and large variability, then again, it is very hard for thermal processes to give rise to that. And the third diagnostic is also the brightness temperature. If the brightness temperature is extremely high, if it is in, we know that nothing in the corona, okay, that corona itself is at about 10 to the power 6 million Kelvin. And we can heat up electrons to maybe something like 10 to the power 7 Kelvin. So the highest temperature lines which we see from the corona, they are at about few times 10 to the power 7. If you have brightness temperatures which are well in excess of that, those brightness temperatures must be produced by non-thermal mechanisms, because there is no plasma which has been heated up to that high a temperature there.
Okay. So we are also differentiating between the radio bus like type 2 and type 3 radio bus. What are we basing our differentiation on? Like, is it on the events they are coming from, or the different frequencies the bursts have?
So when this classification was originally done in about 1950 or so, that was based purely on the morphology of how they appear in the frequency time plane. Okay, so somewhere I think I should be getting close to that. Yeah. So you would notice that these structures look very different in the frequency time plane. Yeah. Where did it go? Here, right? So a type 3 burst looks just like a vertical line here. It has actually a slope of something like order 100 megahertz per second. A type 2 has a much gentler slope. That slope is something like a megahertz or so per second. Both of these guys have fundamental and harmonic components. And so that was the primary discriminant between these, for example, type 2s and type 3s. The others were associations with the flare. So how long after a flare did it take place? What was the part of the band in which it took place? Did it seem to be drifting across frequency in time? So for example, this guy is also drifting in time, right? It has come from, say, something like order 500 or so megahertz to something like 50 or so megahertz in the 30 minutes. So the classification was entirely based on observational data, how these emissions look like in the frequency time plane.
And so you talked about us getting Stokes 5 and Stokes 1 from emission. What is Stokes 1 and Stokes 5?
Okay. So sorry, you know that light is polarized, right?
Yes, sir.
And I need 4 parameters to define the polarization state of radiation. Okay. These are referred to as I, Q, U, and V. Okay. So I stands for total intensity. Q and U stand for the 2 linear polarization, and V stands for the circular polarization, right? Because I have X and Y axes, I can have linearly polarized components along either of these, or I can have, a component along X and a component along Y. So I need Q and U, 2 free parameters to describe the linear polarization, and an additional parameter to describe the circular fraction of the polarization. And so using these IQ, UV, this sort of 4 vector, I can define the complete polarization state of light. So that is what I meant here.
So, and the emissions you are saying, you said that the emissions will be observing, they'll have a temperature of the range of 10 to the power 13 Kelvin of electrons. So
that
are
depends.
Yes.
Okay, complete your question. Yeah.
So is the temperature obtained by the electrons momentary, or do we observe it for a longer time? If so, if we do, then how is it feasible for the electron to stay at such a high temperature when its surrounding is not is at lower temperatures?
So very good. So that's exactly what I was trying to say, that when this temperature is very high, this temperature is temperature of the radiation. This is that if you were to imagine that emission is coming from a black body, that black body would have to be at the temperature of 10 to the power 13. In reality, that emission is not coming from a black body. So there is nothing which is sitting at 10 to the power 13. It is just that the emission is so bright that it appear that if it was really to come from a black body, that black body would have to be very, very hot, 10 to the power 13 Kelvin. So for the non-thermal emission mechanisms, the temperature of the radiation does not correspond to the physical temperature of the medium which is giving rise to the emission.
Thank you, sir.
So all of these different types of bursts, these are all non-thermal. This quiet sun is the only thermal one here. This CME gyrosynchrotron is also a non-thermal mechanism. This is the only thermal mechanism here.
Okay, we have next question.
Yeah, could you explain the radio interferometry part again, especially the last one where you removed some parts of the mirror? I didn't quite get that part properly.
Okay. Okay. So why don't you tell me what you bought first here?
So the first parabolic mirror, the need for the parabolic mirror, I understood that. And the fact that all of the rays are in phase and it comes towards the focus means that they're all coherent, which I understood. But then why remove them? Yeah.
So I never answered the question why remove the mirror, why remove parts of the mirror. If you want to understand why do we need to do that, then you need to think about the fact that what defines the resolution of a telescope? It's lambda by d. Correct? Yeah. Right? Yeah.
Yes.
So so let's say you're working at optical wavelengths. So your lambda is something like, let's say, something like 4,000 angstrom, right? 400 nanometers. If I'm working at a meter wavelength, now my wavelength is much, much larger than the wavelength at optical.
Right.
So something like 10 to the power 8, a difference of 10 to the power 8 in order of magnitude.
Yeah.
So if I was using, say, something like 1 meter class telescope at optical to get some particular resolution, I need a 10 to the power 8 meter telescope to get the same resolution.
Oh, okay.
Right. So now that it is impossible to build a telescope which will be that size, that much in size. Right. So therefore, I have no other option but to say that, well, I can't build a single dish, but what I can do is that I can place pieces of my dish far enough apart that when I cleverly combine the data from that, they will simulate the data from a dish which was that sized.
Okay.
So that is what you are trying to do. That is the trick of interferometry, that it allows you to get a resolution which corresponds to the distance between your individual elements of the interferometer, rather than the size of the mirror of an individual element of the interferometer.
Okay, thank you, sir. I got it.
Okay, any more questions? Yeah.
So the figure that you have shown in different type of radio burst, you told about that type 2 radio burst are generated because of this reconnection and because of this fast shock or CME. Type 3 radio burst are generated because of this open magnetic field lines, electron move in open magnetic field lines. Similarly, what is the source of that type 4 radio burst, type 1 and type 3 storm? That is the source.
Yeah. So the reason I did not specifically talk about that is because there is still no consensus in the community about what is giving rise to them. Slowly, what we feel more and more is, for example, these type 4 bursts. If you are able to look at high time and frequency resolution of type 4 bursts, they don't look like what is shown in here, which is basically a dense or a large featureless blob. This begins to break down into large number of small emissions. Okay, each of these is a little bit like a vertical line. Some of these are not vertical. Some of these are J-shaped or U-shaped or something like that. So what we believe is happening here is that there are a large number of magnetic loops at the base of which or somewhere along which there is some magnetic reconnection activity going on. And this sort of widespread activity is accelerating a large number of independent beams of electrons. These beams of electrons are moving along the magnetic lines of field. They are not open magnetic lines of field because they are not escaping out. They are probably closed lines of field. But the heights of these magnetic loops, they span certain range of heights in the solar corona. And that decides the range of frequencies along which you would see the emissions from that. but there are so many of them which are taking place that we are not able to resolve them individually. They are overlapping, especially when you're looking at this in a spectrograph where you are not able to image them in any way. So it's a superposition of a large number of type 3 like things, but they are much weaker and they are not traveling along open magnetic lines. So that is why they are confined. They have a specific upper limit above which they can't go because they are traveling along closed magnetic loops, and those magnetic loops don't extend to higher heights in the corona. So it's variations of this theme which are giving rise to type 4s and type 3s here.
And what about the type 1 radio burst, the source?
So type 1 is again, so observationally, what we are finding for type 1s is that emission also breaks down into many discrete pieces of emission. If you have sufficiently high time and frequency resolution, they don't seem to be that extended in frequency. They seem to be much more compact in frequency. So it's a bit like, for whatever reason, the electron beam which was giving rise to that was not able to propagate for long distances. It was quenched very quickly, or that beam got thermalized very quickly. Now that could be because those beams are not very energetic to begin with, so it's easy for them to thermalize, or because the environment in which they are moving is maybe especially turbulent or something like this, which is giving rise to that. So there is, like I said, there is not yet a consensus in the scientific community about what exactly is the cause for that here.
And what is the exactly cause for the microwave burst that in the diagram?
So microwave bursts are something similar to type 4s. They are just at much higher frequencies. And so observationally, they were discovered later because there were no microwave telescopes when these things got named. Right? Those telescopes were all at meter wavelengths, and therefore those guys got named till about 300 megahertz or so. And a bit later in time, actually a few decades later in time, as people went to gigahertz frequencies, they also discovered the microwave bursts, which have properties very similar to type 4s.
And sir, is there any type 5 radio burst? Or
there is actually, yeah. In fact, it is marked here right next to type 3.
okay.
Yeah. So again, observationally, these guys are seen at comparatively lower frequencies, usually below 100 megahertz. They are a little bit similar to type 3s, but you find that as you go from higher to lower frequencies, type 3s maintain a fairly well-defined streak, but these guys become much broader. Okay, so it's like, for whatever reason, there is a big dispersion in the electron beam, which is giving rise to this emission. So the emission begins to span a larger spectral scale as you go longer in time.
And also, sir, you have mentioned about Langmuir waves, that Langmuir waves.
Yes.
So what are they?
So Langmuir waves are electrostatic waves. So they are produced in plasma because of some charge separation. So in our context, these Langmuir waves are born whenever you have something called a two-stream instability. So basically, imagine that there is some plasma, and in that there is a stream of electrons which is passing, right? These are the same streams which we are thinking of for type 3s or type 2s or whatever. So as this, stream of electrons is passing through this ambient medium, it gives rise to what is called a two-stream instability. And a part of what happens in response to that is setting up this Langmuir wave, this plasma oscillation in this medium. So you will need a little bit of fluid dynamics and plasma physics to understand that.
Okay, thank you.
The temperature of the corona is about millions Kelvin, and the chromosphere is about 10,000 Kelvin. So you were explaining something about magnetic reconnection and something harmonic frequency. So could you please elaborate it mathematically, like a little bit mathematical hint, like how it can give million-degree temperature?
So how it can give million-degree temperature, that a lot of people are still trying to find out. What people agree on is that the reservoir of energy from where you you must draw this heat to heat up the corona to 1,000,000 Kelvin is the magnetic field, solar or coronal or chromospheric magnetic field. Now the question is, what is in detail, what is the mechanism which is actually extracting this energy from this magnetic field? So there are two leading hypotheses which have been posed. I'm sure you've heard of both of them by now in this workshop. One of them is called the so-called the wave-based heating, which basically says that the base of the photosphere, because of the presence of these convective cells, is always in sort of turbulent motion, and the foot point of all the magnetic field which is emerging into the chromosphere is inside this photosphere. So this magnetic field is constantly being pushed and shoved and jiggled around. And that sets up some waves in this magnetic field. Waves, as you know, can carry energy. And if these magnetic fields can carry energy to these magnetic waves, also called the alpha waves, can carry energy to higher coronal heights, and you are able to find a mechanism to dissipate them, then you have found a mechanism to transport energy from a lower coronal height to a higher coronal height using the magnetic field and heat up the corona. That is one of the most well-regarded hypotheses for coronal heating. The other is what I was referring to as magnetic reconnection. Right? That is basically the nanoflare-based coronal heating model, which Eugene Parker had proposed in 1988. So in that, what is happening is that the picture is the same at the base of the corona, at the base of the photosphere, where this magnetic field is being, is constantly in motion of all sorts. And because of that, this magnetic field has become more and more tangled and braided and so on. And as you probably know, magnetic field has a property akin to tension. Right? The more complicated I make the topology of that magnetic field, the higher tension I build up in that magnetic field, or more energy I dump into that magnetic field. And that process, sorry, go ahead.
That tension means, are you saying about flux freezing type of thing? Like if we...
Yes, this is happening in a flux freezing environment. Yeah.
Okay.
Yeah.
Yeah,
So
then...
if I...
Yeah, continue.
So if I make my magnetic field more and more tangled while respecting flux freezing, I'm investing more and more energy into this, and that process cannot go on indefinitely. At some point, this system has to relax, and that relaxation comes via this process of magnetic reconnection, where if you have a medium whose conductivity is not infinite, and which is the case for the solar corona. So the very small amount of resistivity which is there, because of the presence of that, when oppositely directed magnetic field comes close to each other, it can relax to a lower energy configuration, and the energy it sheds is used to accelerate the electrons or the plasma which is present at the site of the reconnection. It just gives them an instantaneous kick. And that now again, you have taken energy out from the magnetic field and imparted it to the plasma which was present there. So that's the other most promising mechanism for heating up the corona. Right?
Okay,
so
thank you.
I'm sorry, I'm not being as mathematical as you probably would like me to, but this is physically what is happening here.
Divya?
Yeah.
We still have more questions, it seems. So at any point, if you're not available, please let us know.
Yeah,
Okay.
I am fine. Yeah.
Okay.
We can
continue
go
with
on,
the questions then.
Yeah.
Okay. He was first, I guess.
So in the graph you showed like a one plot where the rays are refracted from the surface of the sun. Can you show that again once?
I think I'm going in the wrong direction. It must have been earlier. Anyway,
Yes, yeah, it was earlier, yeah.
Ask your question. Yeah.
Yes, so like in the dynamic spectrograph, when we are looking at different frequencies, you said that the distance of closest approach for different frequencies of the radio waves are different for different frequencies.
Correct. Yes.
And so we are not actually imaging the same height of the corona, right? At different frequency bandwidths when you are looking at it.
Correct.
So how can and so when we spot a source later onwards, you said there was one source which is persistent in different regions of the dynamic spectra. So that is actually different height of the same source, or the same source, like how can we resolve it in the height wise at the 3 dimensions?
Okay, so that's a very good question. So there are a few different things which one has to keep in mind. So if you were making an extremely monochromatic measurement, this is what you are going to see. So one thing which I talked about in a different context, but I did not highlight it here, that what this image shows is a very idealized corona, right? A corona which has electron density distribution which is spherically symmetric. Correct. If that was indeed the case, then this is what you would get. And as you change your frequency, you will go, your distance of closest approach will become smaller or larger. Correct? Yeah.
Yes, sir.
Now, in reality, this corona is not uniform. Like we talked about later about the turbulence in the corona and the density inhomogeneities. And then there is this delta Ne by Ne, which can be, you know, anywhere between a few percent to even 25%.
Yes, sir.
Which means that this ray is actually not going to proceed in this very beautiful, nice curve. It is actually going to random walk its way out.
Yes, you're right.
Because it is going to get refracted by the various inhomogeneities it's going to encounter in the path. Now, those refractions would be much more impactful, or would mostly take place deeper in the corona, because as you come out, the refractive index of the corona becomes closer and closer to 1. And after that, the ray is going to move essentially in a straight line. Right?
Yes, sir.
So keep that thing in mind. And then the other thing I want you to keep in mind is that in the other picture which you're referring to, where I was showing you type 2 sources at different frequencies here, that emission is not very narrow band, in the sense that the fractional bandwidth of that emission, let's say, is spread over something like 20 megahertz or something like that. And the frequency range which we were looking at was something from, I think, from about 130 or so to about 160 megahertz. So basically the emission, what we do believe is that the emission at a given frequency is coming from a region where the electron density corresponds to that particular plasma frequency. Now, wherever this emission is coming from, that region is going to have a range of electron densities because of these inhomogeneities. So any given region is also going to give rise to emission at a larger number of frequencies than what you would imagine in a picture like this.
Yes, sir.
Correct. Now, that's one aspect. Another aspect is that when this electron beam is moving along some direction, now this beam has electrons which are traveling at many different speeds. So the guys which are moving faster will reach further out as compared to the guys which are moving slower. So you find that as these bursts, they drift from higher to lower frequencies, their spectral span increases, because the higher frequency emission is now coming from the faster electrons in the beam, and the lower frequency, sorry, the other way around. The faster electron beams, the faster electrons have moved further ahead and are in regions of lower electron density and are giving rise to emissions at lower frequencies, while the slower guys are still at lower height and they are giving rise to emission at higher frequencies. So all these real life effects come into play, and they sort of make the emission a little more complicated.
Also, another question I have is, for example, the topology of the magnetic field in the corona, like in the does it, like, because like plasma can be taken as a conductor, so does it act like a waveguide for the radio waves? Is it possible?
So it can act. So again, that's a good question. There are instances where that sort of a thing does happen, though it happens in a way different from what one might imagine. So imagine the plasma to be full of magnetic field structures, right? The way you know they are. You also know that the denser the magnetic field is in a given strand, the lower would be the electron density itself, right? Higher is the magnetic field, lower would be the electron density, because that is what is needed to stay in pressure equilibrium. Correct. So now you have these strands of low density, and between them is a plasma which has lower magnetic field and higher electron density. So it is the radiation which is traveling in this outside these strands which gets reflected from the surface of these higher magnetic field strands, and that gives rise to a process called ducting, because of which the emission can sort of, depending on the morphology of this magnetic strand, the emission can be deviated from its true path and might appear at a place quite far away from where it was born.
So like, are there any methods for like computationally correcting for these effects when we're actually reducing the data for images? So are these corrected for, because this such problem I don't think arises in higher like high energy, like in like
Correct,
X-ray
yeah.
or some anywhere else. So
Correct,
for radio images, can we correct for this?
So right now there are no ways to correct for that, because imagine what do you need to correct for it, right? So if you're trying to correct for things like scattering, right? Scattering. So let me go to a different example. So you're familiar a little bit with optical astronomy, right? If you look at a star at night, it appears much larger than what its true size is if you're looking at it from the Earth, and that's because of the atmospheric turbulence, right? The so-called seeing of the atmosphere. So in effect, what you are saying is that I want to correct for the seeing sort of an effect, which is happening because of coronal turbulence, right? Now that is not really feasible to correct for in the solar context right now. That is feasible to correct only in a statistical sense, where you say that, okay, I'm going to do a simulation where I'm going to shoot a large number of rays from this through this medium and see what do they appear like. And using this, I'm going to characterize my medium, that if I had a source like this, it is going to appear like this. And the displacement of that source from its true position is going to be so much. And this is the amount by which that displacement is going to change as a function of frequency. So those things you can do. So in your observations, you can, for example, look at how the location of the source is changing as a function of frequency, and then try to build a model which will replicate that and use it to say that these must be the micro properties of my medium to give rise to the observations which I'm actually measuring.
Okay, sir. Thank you.
Yeah.
Hello, sir.
Yes.
If I have to find out like whether nanoflare is participating in coronal heating or not, then what will be the condition and power law index, and how we will arrive at?
Okay, so so whenever you are going to go to study nanoflares, naturally you will have to look at a statistically large sample of them, right? Because you would want to look at their power law as a function of their intensity. You want to look at sorry, where are they taking place on the sun, right? Are they associated with anything else? Can I find a signature in EUV or X-ray or something like that? So those would be the sorts of things which you would want to do. What we've been finding is that what we can observe at radio frequencies, they are much weaker than what it is possible for the current instrumentation to see in X-rays or EUV. Okay. So right now we have only radio signatures and we don't have any signatures in other wavebands. So to see whether or not these nanoflares, the radio signatures of nanoflares which we are seeing, if they are responsible for coronal heating or not, what you will have to do is you will have to rely on simulations. What you will have to do is to say that, okay, let me try to simulate a collection of nanoflares such that the radio signatures they produce are similar to what I see in my data. And using that, you will try to estimate that, okay, how much energy do these nanoflares dump in my corona? And is that sufficient to heat it up to what we see or not? So that's broadly what you will end up doing. The problem is a little complicated because these somewhere between 10 to the power minus 6 to 10 to the power minus 9 of the energy of the nanoflare is what is radiated as electromagnetic radiation. So it's 1/millionth at the best. And from that 1/millionth, you are now trying to reconstruct what the full quantity is going to be. And it involves a sort of nonlinear process. Because this is a coherent emission, its growth is nonlinear in nature. So it's very sensitive to initial conditions which you use in your simulation. So we are working on a project to try to model that and see what answers it leads to in terms of the energy flux dumped into the corona. And it's a statistical modeling approach, which basically one has to take.
Okay, sir.
Is there a question behind from that? Yes.
Hello, sir.
Hi.
Sir, you were talking about type 3 bursts, if I understand that correctly.
Yeah.
And you were talking about some QPOs in that context. Can you please repeat what the conclusion from that slide was?
So what you should think of from that essentially is that the beams which are giving rise to those type 3s, you should really think of those as test particles, right? So I've basically released some test particles in my system, and I'm going to try to investigate properties of my system using these test particles. Okay, so the electron beam, which is this is the plot you were looking for. So the electron beam, which is sort of lighting up this magnetic field as it is going along, lighting up in the sense that as it is moving, the place, whatever is the local plasma frequency, that is where the emission is occurring. And what you find is that this thing seems to be oscillating like this. When it is becoming smaller, it is becoming brighter. When it is becoming larger, it is becoming a bit fainter. Right. So now you are wondering what is giving rise to this oscillation. Simplest solution which one would have thought of is that there is some sort of a sausage mode, right? If you think of how fast this thing is traveling, in the sense that how fast is the emission moving from one frequency to another frequency, which is a measure of the height in the corona, right? Because this frequency corresponds to the local plasma frequency, which corresponds to square root of the local electron density. So I can roughly associate a height for each frequency. So if I look at the delta H by delta T, how fast it has to move, then and compare that to the size of this oscillation, right? Because I've measured the size of the source, I know how large it is when it has expanded to its full amplitude, and how large it is when it has become contracted. This oscillation, the speed with which it needs to oscillate, is about 100 times the local Alfvén speed. So clearly it could not be the plasma which is moving this way. It is like there is a cone of emission sitting at the bottom, which is expanding and contracting, and which is lighting up different parts of this magnetic field strand as this beam of electrons is going up.
Okay, sir. Thank you. Just one more question.
Sure.
You showed us a area versus time graph in the context of turbulence, and you pointed that we could measure or quantify the electron density in homogeneity in
Correct.
that case.
Yeah.
Can you please point out how we can do that? I mean,
right. Yeah. So I'll briefly give you a sense for how one can do that, because that is I did not really cover that here in any detail. But the picture I was trying to paint for you, that I think you will get. So I have a point source of emission, which I switch on at some particular time. Before that, there was no source. Now suddenly there is a source, right? It's like a step function. And on the other side, sitting on the Earth, I'm looking at the source and I'm imaging it with pretty high time resolution. If this radiation has to pass through some turbulent medium, okay, let's go back. If there was no turbulence in this medium, if it was all uniform isotropic medium, then I would see the light source to switch on in exactly the same manner as it switched on at the source. Correct? Yeah. Yes, agree? Yeah.
yes, sir.
Okay, perfect. So now if I introduce some turbulence in this medium, what will happen is that, yeah, but some of the light rays would travel straight without being reflected or refracted by the turbulent structures here. But some of them will get refracted. They'll wander around and take longer paths to get to me. Correct? Because they are going to take longer paths, they are sorry, the other way around. They are going to take longer time because they have wandered further away from being a straight line path.
Yes, sir.
Because they have wandered further away from being a straight line path, the apparent size of the source would seem to increase to me as a function of time. Right? The longer I wait, the rays which have gone even further away would be able to reach me.
Yes, sir.
Now, what that straight line is trying to model is what is the delta NE by NE which I need to produce this rate of growth of the size of the source. the stronger is my inhomogeneity, the steeper that line will be, right? Rather than being like this, it will turn this way, right? You will end up drawing a line like this. If I have more inhomogeneity, if I have less inhomogeneity, the line will be shallower. If I have no inhomogeneity, this would be a straight line with slope 0.
Okay. Okay.
So that is the idea behind there.
Okay, sir. Thank you very much. So when you talked about a crystal where you got the linearly polarized light, so in similar to that, even this, I don't know, like circularly polarized light as it travels through the medium, even there the amplitude can change and then the polarization can change. So if that's the case, so what makes this linearly polarized light, exotic or special compared to
So good question. So for the circularly polarized light, what would change essentially is the phase relationship between the two, between the RCP and the LCP, between the right and the left circularly polarized light, right?
Yes.
It would not destroy the polarization of the light. So whatever fractional circular polarization you start with, you will exit with the same fractional polarization, except that the phase between the LCP and RCP would have changed.
Sir,
Right?
yes.
For linear polarization, what happens is that now I'm going to experience some Faraday rotation. That Faraday rotation is essentially lambda squared times the rotation measure which I have. That rotation measure is sort of B dot ds integrated over the line of sight. Right? Now, for the corona, this rotation measure is so large that even if I'm looking at very nearby frequencies, I'm still observing a phase change greater than pi by 2, or in fact, maybe even many cycles of pi between them. So any real life measurement which I'm making is going to average over some narrow band, maybe 10 kilohertz, maybe 1 kilohertz, something like that. So even across that 1 kilohertz, it would have, the different rays would have gone undergone such different Faraday rotations that if I was to superpose them all, I'll end up with nothing. The net polarization will drop to close to 0. That is the argument there. And the resolution to that fallacy or whatever is that that argument is perfectly true. If the linear polarization was born that deep in the corona, it would not survive to us. So the resolution to this of how come there is linear polarization in this emission is that this linear polarization is actually not born at that place. It is picked up because of propagation effects at much higher coronal heights. And what we are investigating is that because we have this density turbulence in the corona, and in fact, if you look at observations from one of the payloads on board Parker Solar Probe called Whisper, which is looking at the corona in great detail, they find that it is not uncommon to have even an order of magnitude denser systems or plasma clumps in the corona. So it is possible for reflections to take place from this denser corona. And if you are able to meet the appropriate conditions for this Brewster, the reflection at Brewster angle, then you are going to get linearly polarized light after reflection. So those are the things which, that's the sort of things which we think are giving rise to this. And in fact, linear polarization has been seen in stellar flares from other stars also, at least in one case, UV SETI for that at 170 megahertz using LOFAR, people have seen linear polarization during a solar flare. And for a different star, they have seen linear polarization again from a stellar flare at much higher frequencies at about a gigahertz or so. And those guys are also thinking along the same lines for the what is giving rise to this linear polarization.
Yes, sir. So just one more question. So in case of one result where you show that you showed that suddenly there is a Stokes V parameter coming because of the CME. So what causes this, sir? Like before that there wasn't a Stokes V parameter, but then
Correct,
suddenly.
yeah. So the Stokes V was there. It was just that it was so weak that it could not be measured. I guess that's sorry, I think I'm going in the wrong direction. But so anyway, I get your question. So the reason what gave rise to that Stokes V was the much stronger magnetic field which was present during that CME. If that magnetic field was missing, you would not see the Stokes V emission which you are seeing here. That's the point which these guys were making as well. So because of two reasons, enhanced magnetic field and enhanced electron density due to the CME plasma, the Stokes-V emission became measurable.
Okay, sir. Thank you, sir.
All right, let's break now. Thank you very much, Professor Divya again. So let's thank
Sure.
him again.
Sure. Thank you so much. And I hope you enjoyed the talk and will enjoy the rest of the workshop as well. Thanks a lot and take care. Yeah. Goodbye.
Thanks again. Thanks again for joining.
Sure. So I'll stop
Okay.
sharing and log out. Yeah.
Sure. Thanks. Okay, so we take a break now. So there is a slight change in the program. So the Vaibhav talk, we will have it in the afternoon. So you all will be doing your project time after the break, after the tea break. And then you continue the projects after the lunch break, and Vaibhav will take last 1.5 hours or so. Okay. All right. All of you are signing that sheet, attendance sheet, right? Okay. Please pass it along to Sanmoy, that sheet. Okay. All